Hi guys. Now, in a previous video, we talked about the energy of a parallel plate capacitor. And what did we conclude? We concluded that if there is a capacitor, right, and let us say each sides of the plate have area A, the distance between them is D, right? And let's say the charge is Q minus Q, then we said that the energy, right, the potential energy of the system, the U, is going to be equal to 1 by 2 Q into V, and since Q equals CV, I can also write this as half CV square, or this is equal to 1 by 2 Q square, or I can write this as 1 by 2 Q square upon C, right? This Q square upon 2C, right? It will be is equal to Q square upon 2C. So all of them say the same thing using different variables. Now one question, kind of sounds like a philosophical question I'll pose to you, is that when we pull this apart, hypothetically, right, we can actually send some charge through a battery, and the end result is same. So it will have the same energy, right, regardless of how this charge plus Q and minus Q came about on these two plates. Right? Now, the question I have for you is, right, you could ask a question, so where is this energy stored, right? Can we say that the energy that we gave, this energy is stored, so to say, stored somewhere? Now let's try to see if we can develop some intuition around it, right? Now let us say in the previous previous videos we said that okay, if the two plates were together, right, just barely touching, right? So effectively plus Q minus Q they would be practically together, right? So which means they would cancel each other, right? So which means there is no charge. If there is no charge, what happens? If the two plates are together, the two plates are practically together, then there is no charge. Effectively, they'll cancel, no charge. So no charge means, right? Which means there is no electric field. No electric field. Okay. Now when we pull them apart, right, and by whatever we get them into this configuration, now there is electric field. Where is the field? The field is inside this. In what direction? The field is it's a uniform field, right? And it will be in this direction, right? These will be the field lines, right? And so on, right? I'm not drawing all of them. Okay. So now the question is, earlier there was no charge when they were together. Practically there was no charge, and there was no energy, right? We took that as the zero potential energy, and then when you pulled it apart, now there is this electric field, right? And now the system has got energy, right? So one way to think about it is we can say that this energy, right? This energy is stored in the electric field, right? This electric field has energy, and this is energy stored there, right? So the question I'm going to ask you is, how much is the energy stored per unit volume, right? Very simple. What is the energy, right? Energy per unit volume. If you are saying that this energy is in the electric field, then what is energy per unit volume, right? For electric field, for electric field. Okay. So then we can say, okay, fine, we have the total energy, let's divide. The electric field is only in this area, it's not anywhere outside, right? It's only in this area. So which means we can say, okay, take the total energy. If I divide by this, by the way, when I say area, I don't mean area, I mean this particular enclosed volume, right, between the two plates. So if I take this energy and divide by this volume between the plates, I will get the energy density, so to say, for the electric field. So I'll call this energy density, right? So we'll say energy density, right, which is energy per unit volume, same thing, right, will be equal to this upon volume. So I can say that this would be, let's try this, 1 by 2 QV, right, and this upon volume. So what is the volume? Volume is going to be this area into distance d, would be A into D, right? Now I can write this as half CV square, right, this thing. So it will be 1 by 2, or let me write this as CV square, right, upon 2AD. Now, what is the capacitance here? Capacitance here is going to be epsilon naught A upon D, right? So there are two things I would like to substitute. So one is I want to find the energy density of the electric field, right? But there is no electric field here, right? So what is the relationship between the variables here and electric field? So I have two goals. One objective is I want this expression in terms of electric field, right? And second, I don't want the capacitance. I don't want to use C. I want to actually put the value of capacitance here, right? Because I know what is the A, I know what is the D, I know the way it's a parallel plate capacitor. So I know what C is. So I'll just put the value here. So second is we'll put value of C. Put value of C because I want the answer in terms of A, D, etc. Not C is just a term, and we know we need to put the value there, right? Put value of C. So let's do that. So first, what is going to be V in terms of electric field? So we know that, right? We know that here, since the field is constant, right? My magnitude, right? Magnitude V is going to be nothing but E into D, the magnitude, right? Okay. So now I'll put the magnitude here as well, right? So now what is my so what will E be? So magnitude of E is going to be nothing but V upon D, right? Or V is equal to E into D, right? Either of those. So now I can put this here. So we'll say energy density is equal to first C. C is equal to what? Epsilon naught A upon D, right? C is equal to epsilon naught A upon D, and so let me write this. So C equals epsilon naught A upon D into V square, right? And what is V square? V square is equal to, V is equal to ED. So this would be E square into D square. So this is CV square and then divided by 2 into A into D, right? So now let's cancel out some of the common terms. So this A and A gets cancelled, and here we have D square, D and D, D square, and here D square. So this and these terms will cancel, and then finally what we have? We have this is equal to 1 by 2 epsilon naught E square, right? Very simple, beautiful result, right? So energy density, right? Energy density, this is equal to half epsilon naught E squared. So very simple, very beautiful relationship, right? And you'll see that, it's very similar to half mv square kinetic energy, half I omega square, for rotation motion and so on, right? Very similar equation. Now, one last thing, right? Here we said this is the energy density of what? Of electric field. Energy density of, reminder, this is for electric field, right? Now, this was for a special case of a parallel plate capacitor, but I'm going to now state it. I'll not prove it to you. I'll just state it that this is true for any electric field, right? So it doesn't matter what the configuration is. If there is some electric field present, right? If somebody says, I know the electric field at this point, what is the density per unit volume? It is going to be half epsilon naught E square. Okay? Thank you very much.